welcome to this problem walkthrough. Today, we'll be exploring LeetCode problem number 1494, Parallel Courses 2. This is a fascinating problem that challenges us to optimize the number of semesters required to complete a series of courses while adhering to specific prerequisites. Let's dive in and break it down step by step. In this problem, you are tasked with scheduling courses in a way that minimizes the number of semesters needed to complete all of them. You are given n courses, labeled from 1 to n, and an array called relations. Each element in relations represents a prerequisite relationship between two courses. For example, if a pair, Prev course, Next course, is given, it means you must complete Prev course before you can enroll in Next course. Additionally, there is a limit of k, which specifies the maximum number of courses you can take in a single semester. Your goal is to determine the minimum number of semesters required to complete all n courses, or return -1 if it's impossible due to circular dependencies in the prerequisites. The output of this problem is an integer representing the minimum number of semesters needed to complete all courses. If there's a cycle in the prerequisite relationships, meaning some courses depend on each other in an unresolvable loop, the output should be -1. For instance, consider this first example. If n is 4, relations is 2, 1, 3, 1, 1, 4, and k is 2, you can complete the courses in the following sequence. In the first semester, you take courses 2 and 3 simultaneously, since there are no prerequisites blocking them. Then, in the second semester, you can take course 1 because its prerequisites, courses 2 and 3, are already completed. Finally, in the third semester, you take course 4 after completing its prerequisite, course 1. Therefore, the minimum number of semesters required is 3. Let's now look at another example. Suppose n is 5, relations is 2, 1, 3, 1, 4, 1, 1, 5, and k is 2. In this case, you can take courses 2 and 3 in the first semester. Then, in the second semester, you take course 4, as it is independent of other courses being completed. In the third semester, you can take course 1, but only after its prerequisites, courses 2, 3, and 4, are completed. Finally, in the fourth semester, you take course 5, which depends on course 1. Therefore, the minimum number of semesters required to complete all courses is 4. Now consider a scenario where n equals 3, relations is 1, 2, 2, 3, 3, 1, and k is 2. In this case, it is impossible to complete all the courses because the prerequisites form a cycle. Specifically, course 1 depends on course 2, which depends on course 3, which in turn depends back on course 1. The circular dependency means there is no way to start or finish any of the courses, so the output for this case would be -1. Identifying and handling cycles is an important part of solving this problem. To summarize the constraints and edge cases you need to consider, n is between 1 and 15, and the number of prerequisite pairs in relations is limited to a maximum of 100. All prerequisite pairs are unique, and the value of k, the maximum number of courses you can take per semester, is between 1 and n. Some important observations include, if k is greater than or equal to n, you can complete all courses in a single semester, provided there are no prerequisites blocking them. If there are no prerequisites at all, the minimum number of semesters is simply the ceiling of n divided by k. Lastly, if k equals 1, you can only take one course per semester, so the total number of semesters required will be determined by the length of the longest chain of prerequisites. These constraints and edge cases will help guide your approach to solving the problem efficiently. To solve this problem, we initially consider a brute force approach, which is conceptually straightforward. The idea is to generate all possible sequences of course completions that respect the prerequisite constraints, and then divide these courses into batches of up to k courses per semester. This involves recursively exploring all subsets of courses, ensuring prerequisites are satisfied before including a course in any batch. While this method is simple to understand, it is computationally infeasible for larger inputs because of its exponential time complexity, approximately 2 to the power of n*n. For example, when n is 15 or higher, the number of states to explore grows too rapidly, making this approach impractical for real-world use. To address these challenges, we shift our focus to a more optimized solution that leverages bit masking and dynamic programming. Here, we make several key observations that help simplify the problem. Each course can be represented as a single bit within a bitmask, where a 1 indicates the course is completed, and a 0 indicates it is not. This representation allows us to treat the problem as finding the shortest path in a state space, where each state corresponds to a unique bitmask of completed courses. Additionally, the prerequisite relationships, which form a directed acyclic graph or DAG, enable us to identify courses that can be completed in the current semester, those without any unmet prerequisites. By iterating through subsets of courses, we can determine valid groups of up to k courses that can be taken in parallel in a single semester. Building on this foundation, we refine the optimized approach further. First, we pre-compute which courses are available for any given set of completed courses by checking the prerequisites. This speeds up the process of determining valid courses for each state. Next, for every state represented by a bitmask, we iterate over all subsets of valid courses, up to a maximum of k, and transition to a new state by marking those courses as completed. Using dynamic programming, we maintain a table dp mask to store the minimum number of semesters required to reach each state. The goal is to minimize the number of transitions needed to reach the final state, where all courses are completed, represented by the bitmask 1n1. In terms of complexity, this approach involves 3 to the power of n*n operations, where 3 n accounts for iterating over subsets of courses, and the factor of n arises from validating prerequisites. While this is significantly more efficient than brute force, it still requires careful management of state transitions. An alternative strategy in certain cases is to utilize topological sorting, which works particularly well when k is large relative to n. In such scenarios, all available courses can be taken in a single semester without exceeding k. This method involves grouping courses into semesters based on their topological order and has a time complexity of n plus m, where m represents the number of prerequisite relationships. However, this approach is less flexible for smaller values of k, making it suitable only for specific problem constraints. Given the trade-offs among the different approaches, we choose to proceed with the bitmasking and dynamic programming strategy. This method strikes the right balance between efficiency and flexibility, making it well-suited for a variety of input constraints, such as different values of n and k. The key insight here is that representing states as bitmasks reduces the problem to a manageable state space search. By incorporating dynamic programming, we eliminate redundant computations and ensure that the solution is optimal. While implementing this approach is more complex than brute force or even topological sorting, the performance improvements justify the additional effort. This strategy is robust enough to handle strict constraints, such as when k is small, and scales effectively for larger inputs. In conclusion, leveraging bitmasking and dynamic programming allows us to achieve an optimal balance between scalability and time complexity. While alternative approaches like brute force are too slow, and topological sorting is too restrictive, our chosen strategy provides a comprehensive solution to the problem, ensuring both correctness and efficiency across diverse scenarios. This problem revolves around scheduling courses under specific constraints. Imagine you have a set of courses to complete, but some courses have prerequisites, meaning you can't take certain courses until others are finished. Additionally, there's a limit on how many courses you can take in a single semester. This creates a graph-based scheduling problem where we need to decide the order of taking courses while minimizing the number of semesters required. To solve this, we start by modeling the courses and their dependencies as a directed acyclic graph, or DAG. Each course becomes a node, and if one course is a prerequisite for another, we add a directed edge between them. The adjacency list representation of the graph makes it easy to track which courses depend on which others. At the same time, we use an in-degree array to count how many prerequisites each course has. This helps us identify courses that can be taken immediately, as they will have an in-degree of 0. Now, we apply a topological sorting approach with the additional constraint of limiting the number of courses per semester. We use a queue to manage the courses with no prerequisites, and we initialize a counter, semester_count, to keep track of how many semesters have passed. During each semester, we increment this counter and process up to k courses from the queue, where k is the maximum number of courses allowed per semester. For each course processed, we decrement the in-degree of its dependent courses. If any dependent course's in-degree becomes 0, it is added to the queue, making it eligible for the next semester. This process continues until all courses are processed. Once no courses remain in the graph, the value of semester_count gives us the minimum number of semesters required to complete all the courses. This approach works because of several key insights. First, topological sorting ensures that prerequisites are always completed before their dependent courses. This is critical for maintaining the dependency rules given in the problem. Second, the use of a queue allows us to process courses in layers, effectively simulating semesters. Courses with an in-degree of 0 represent the ones ready to be taken in the current semester, and as we process them, we make room for others in subsequent semesters. Finally, the batch constraint limiting the number of courses to k per semester is enforced by processing only up to k courses from the queue during each iteration. These elements work together to solve the problem efficiently while respecting the rules of both prerequisites and semester limits. To implement this algorithm, we rely on three primary data structures. First, the adjacency list represents the graph, where each course points to the list of courses that depend on it. This structure is both space-efficient and easy to traverse, with a complexity of O, V plus E, where V is the number of courses and E is the number of prerequisites. Second, the in-degree array helps us quickly determine which courses have no remaining prerequisites. Each entry in the array corresponds to a course, and its value indicates how many prerequisites are still required. This array also has a space complexity of O, V. Finally, the queue stores courses with an in-degree of 0, making them eligible for the current semester. The queue operates efficiently, and its space complexity is O, V, since it only stores courses ready to be processed. Analyzing the complexity of this algorithm gives us insights into its efficiency. The time complexity is O, V plus E, as we process each course and each prerequisite exactly once. The space complexity is O, V plus E, as well, due to the adjacency list, in-degree array, and queue. Several edge cases must also be considered. For example, if the graph contains circular dependencies, it will be impossible to complete all courses. This can be detected if nodes with non-zero in-degrees remain after processing. On the other hand, if there are no prerequisites, all courses are independent, and the minimum number of semesters will be the ceiling of V divided by K. Another scenario occurs when the number of courses eligible for a semester exceeds K. In this case, the algorithm ensures that courses are appropriately distributed across multiple semesters while adhering to the batch constraint. Lastly, there are optimizations that can enhance the algorithm. One such optimization is early termination. If the queue becomes empty before all courses are processed, it indicates the presence of a cycle in the graph, and the algorithm can terminate early. Another optimization involves using a priority queue to prioritize courses with fewer dependencies. By processing these courses earlier, we may be able to reduce the total number of semesters required in some cases. These adjustments can make the algorithm more efficient or adaptable to specific variations of the problem, ensuring that the solution remains robust and optimized for different input conditions. To solve the problem, we start by importing the necessary modules. The default dict from the collections module helps us build the adjacency list representation of the dependency graph, and deque will be useful for potential queue-based operations. Within the solution class, the min number of semesters function begins by pre-processing the input. Here, we construct a graph to represent the course dependencies and calculate the in-degree of each course, which tells us how many prerequisites each course has. Dependencies are adjusted to zero-based indexing for easier manipulation. Next, we initialize a variable all_courses as a bit mask to represent all courses, where each bit corresponds to a course. We also create a dynamic programming array dp to store the minimum number of semesters needed to reach any given state. Initially, dp0 is set to 0 because no semesters are needed to complete 0 courses. Then, we pre-compute a prereq_mask for each course, which encodes its prerequisite courses as a bit mask. This allows us to efficiently check whether all prerequisites for a course are satisfied in any given state. Finally, we set up the main dynamic programming loop to iterate through all possible course states. Within the dynamic programming loop, we determine which courses are available to be taken in the current state. A course is considered available if it is not yet completed in the current state and all of its prerequisite courses are satisfied by the current state. These available courses are collected into the available list. Next, we generate all possible subsets of up to k courses from the available list. Using bitmask operations, we count the number of courses in each subset and skip subsets that exceed k courses. For valid subsets, we compute the next underscore state by adding the selected courses to the current state. The DP value for this next underscore state is updated to the minimum of its current value and the DP value of the current state plus 1, representing an additional semester. At the end of the loop, the result is stored in DP, all underscore courses, which represents the minimum number of semesters required to complete all courses. This value is returned as the final result. Here, we start by importing the necessary Java utilities and defining our solution class. The main function, min number of semesters, takes three inputs: the total number of courses n, the dependencies array indicating prerequisite relationships, and k, the maximum number of courses that can be taken per semester. To manage these dependencies, we first build an adjacency list called graph and an in-degree array to track the number of prerequisites for each course. Each course initializes its own empty list in the graph, setting up the structure to represent dependencies. Then, for each dependency pair, we decrement both course indices by 1 for zero-based indexing and populate the adjacency list and in-degree array. This pre-processing step helps us efficiently track which courses are ready to be taken. Next, we initialize the all courses bitmask to represent all courses being completed, and a dynamic programming array DP where each state represents a subset of completed courses. Initially, DP 0 is set to 0 as no semesters are needed to complete 0 courses, while all other states are set to infinity. Finally, we pre-compute a prereq mask for each course, storing the bitmask of all its prerequisites. This enables us to quickly check if a course can be taken based on the current state. Now, we calculate the prereq mask for each course by iterating through the graph. For every course and its next courses, we update the bitmask of prerequisites using bitwise or operations. This ensures that each course's mask reflects all the courses that must be completed before it. With this setup complete, we move into the dynamic programming phase using a bitmask approach. Here, we iterate through all possible states, where each state represents a subset of completed courses. If the current state is not achievable, we skip it. For achievable states, we identify the list of courses that are available to take next. A course is available if it is not yet completed in the current state and all its prerequisites are satisfied in that state. These available courses are stored in a list, allowing us to efficiently generate subsets of courses to take next. For each subset of available courses, we ensure that the number of courses in the subset does not exceed the maximum allowed per semester, k. If the subset satisfies this constraint, we compute the next state by marking the courses in the subset as completed in the current state. Finally, we update the dynamic programming array for the computed next state. By comparing the existing value of DP, next state, with DP, state, plus 1, we ensure that the minimum number of semesters required to reach this state is stored. This update is repeated for all valid subsets of available courses, systematically exploring all possible paths to complete the courses. After processing all states, the result is stored in DP, all courses, which represents the minimum semesters needed to complete all courses. This value is returned as the final output. Overall, this implementation efficiently balances the constraints of prerequisites and the maximum courses per semester using bitmasking and dynamic programming. To solve this problem, let's start with a minimal example where there are two courses, labeled 1 and 2, and a dependency that course 1 must be taken before course 2. Additionally, only one course can be taken per semester. First, we pre-process the data to make it easier to work with. We represent the courses as nodes in a graph, so we build a graph where course 0 points to course 1. We calculate the in-degrees, which tell us how many prerequisites each course has. In this case, course 0 has no prerequisites, while course 1 has one. We also pre-compute prerequisite masks, which help us determine if the prerequisites for a course have been satisfied. For example, course 1 depends on course 0, so its mask is 1. Next, we initialize our dynamic programming array. We represent all courses using a bitmask, where 0 means a course is incomplete and 1 means it's completed. For two courses, all underscore courses is represented as binary 11. Our DP array starts with DP 0, set to 0, meaning no semesters are needed when no courses are completed, and the rest are set to infinity because those states are initially unreachable. Now, let's walk through the state transitions for this example. Starting with state 0, where no courses are completed, course 0 is available since it has no prerequisites. We generate subsets of available courses to determine which courses can be taken. Taking course 0 corresponds to the subset 1 in binary. This results in a next underscore state where only course 0 is completed, and we update DP1 to 1 semester since it's the minimum between infinity and DP0 plus 1 semester. Next is state 1, where only course 0 is completed. Here, course 1 becomes available because its prerequisite, course 0, is satisfied. Taking course 1 corresponds to the subset 1 in binary, resulting in a next underscore state where both courses are completed. We update DP3 to 2 semesters. Finally, in state 3, all courses are completed, so no further action is needed. The minimum number of semesters to complete all courses, stored in DP, all underscore courses, is 2. Let's consider a larger example with 4 courses and dependencies such that course 1 must be taken before courses 2 and 3, and course 3 must be taken before course 4. This time, up to 2 courses can be taken per semester. First, we pre-process the data. The graph shows that course 0 points to courses 1 and 2, and course 2 points to course 3. We calculate the indegrees, where courses 1, 2, and 3 each have 1 prerequisite, and course 0 has none. The prerequisite masks indicate which courses each course depends on. For example, course 3 depends on course 2, so its mask is 4 in binary. We initialize our DP array, starting with DP0, set to 0 and the rest set to infinity. Since there are 4 courses, all underscore courses is represented as binary 1111. For state transitions, we begin with state 0, where no courses are completed. In this state, only course 0 is available, as it has no prerequisites. Taking course 0 corresponds to the subset 1 in binary, resulting in a next underscore state where only course 0 is completed. We update DP1 to 1 semester. In state 1, where only course 0 is completed, courses 1 and 2 become available because their prerequisite, course 0, is satisfied. Here, we can take up to 2 courses per semester. Taking both courses 1 and 2 corresponds to the subset 3 in binary, resulting in a next underscore state where courses 0, 1, and 2 are completed. We update DP7 to 2 semesters. In state 7, where courses 0, 1, and 2 are completed, course 3 becomes available. Taking course 3 corresponds to the subset 1 in binary, resulting in a next underscore state where all courses are completed. We update DP15 to 3 semesters. At this point, all courses are completed, and the minimum number of semesters required is stored in DP15, which is 3. For a final example, consider an edge case with 3 courses and no dependencies, where up to 2 courses can be taken per semester. Here, all courses are available from the start. From state 0, we can take up to 2 courses, completing states 3 and 7 by the second semester. The DP array reflects that all courses can be completed in just 2 semesters. This demonstrates how the approach adapts to scenarios with no dependencies, optimizing the number of semesters based on the constraints. In this problem, we use a dynamic programming approach combined with bit masking to solve the scheduling challenge efficiently. First, during preprocessing, we construct the adjacency list and integree array to represent the dependency graph. This step ensures we can quickly access prerequisite information for each course, and it takes m time, where m is the total number of dependencies. Additionally, we pre-compute a prereq_mask array, which helps us efficiently determine which prerequisites are needed for any given course. This pre-processing step also takes m. Next, we move to the bitmask dynamic programming iteration. Here, we represent each possible combination of completed courses as a bitmask, leading to 2 to the power of n states in total, where n is the number of courses. For each state, we examine all courses to determine which ones are available to be taken next, a step that requires n time. These 2 components set the foundation for our overall approach. Now, let's consider how we handle the subsets of available courses. For each state, we generate all possible subsets of the available courses, allowing us to evaluate combinations of up to k courses that can be taken in a semester. If the size of the available courses is x, the number of subsets is 2 to the power of x, with x being at most n in the worst case. Generating and processing each subset involves updating the next underscore state, which takes n time. This means the total time for subset generation and processing is 2 to the power of n asterisk n. Combining this with the dp states, we arrive at the overall dp computation time. For each of the 2 to the power of n states, we process subsets, leading to a worst-case complexity of 4 to the power of n asterisk n. Finally, when we combine all steps, including pre-processing and dp computation, the overall time complexity becomes m plus 4 to the power of n times n. This accounts for both the dependency graph and the exponential growth from the bitmask dp. When analyzing space complexity, we start with the graph representation. The adjacency list used to represent dependencies requires m space, proportional to the number of edges in the graph. Additionally, the in_degree array and prereq_mask array each require n space, corresponding to the number of courses. The dynamic programming array, which stores the minimum semesters for each state, is the most space-intensive component. With 2 to the power of n states, the dp array requires 2 to the power of n space. Beyond this, we use temporary space such as the available list, which holds up to n courses, requiring n space. Temporary variables used during subset generation and state transitions are relatively insignificant in comparison to the dp array. Summing these components, the overall space complexity of the solution is m plus 2 to the power of n. This balance of space usage ensures the solution remains feasible for moderate values of n. Comparing this approach to a naive solution highlights the efficiency gains achieved. A brute force method would attempt all possible ways to schedule courses across semesters, checking every combination of subsets for all semesters while adhering to prerequisites and the limit of k courses per semester. This exhaustive search leads to a time complexity of n, which is computationally prohibitive for larger values of n. In contrast, the optimized dynamic programming solution with bit masking reduces the complexity to 4 to the power of n asterisk n. While still exponential due to the 4 to the power of n term, this is a significant improvement over the factorial growth of the naive approach. However, the trade-off is that the dp method requires additional space for the dp array, which is 2 to the power of n, and it remains computationally expensive for large n. This illustrates how the optimized approach balances efficiency and feasibility for the problem's constraints. To better understand the performance of the solution, we can analyze the best, average, and worst-case scenarios. In the best case, where there are no prerequisites for any course, the bitmask dp still iterates over all 2 to the power of n states. However, the absence of dependencies simplifies the processing of available courses, leading to a time complexity of 2 to the power of n asterisk n. On the other hand, the average and worst cases are effectively the same in this problem, as the computation always involves evaluating all 2 to the power of n states and generating subsets of available courses. The worst case, with the maximum number of dependencies, does not change the asymptotic complexity but may slightly increase constant factors. Mathematically, the exponential complexity arises from subset generation for each state. With 2 to the power of n states and up to 2 to the power of n subsets per state, the time complexity includes a dominant 4 to the power of n factor. For space, the dp array of size 2 to the power of n dominates the overall complexity, reflecting the trade-offs inherent in the approach. In conclusion, the dynamic programming solution with bit masking offers a practical method for scheduling courses within the given constraints. It effectively balances computational complexity and space requirements, making it suitable for moderate values of n, such as n less than or equal to 15. While the exponential time and space complexities make it impractical for very large n, the solution is significantly more efficient than a brute force approach, reducing the complexity from n to 4 to the power of n asterisk n. By leveraging preprocessing, bitmasking, and subset generation, this method efficiently handles the problem's constraints and provides a clear path to determining the minimum number of semesters required to complete all courses while adhering to prerequisites and k-course limits per semester. When tackling this problem, there are several common pitfalls to watch out for. First, ignoring cycles in the prerequisites graph can lead to solutions that assume all courses are completable, which is not true if there's a circular dependency. To address this, you should validate the graph for cycles using methods like Kahn's algorithm or a depth-first search with a visited set. Next, implementing topological sorting incorrectly can cause major issues. For example, if you forget to decrement the in-degree of dependent nodes after processing a course, the algorithm might fail to terminate or give incorrect results. Always ensure that you update the in-degree and add courses with 0 in-degree to the processing queue. Another mistake is not properly handling the limit on how many courses can be taken in parallel, which is a key aspect of this variation. To fix this, adopt a greedy or BFS-based approach to select up to the allowed number of courses per semester. Finally, inefficient data structures, like using an adjacency matrix instead of an adjacency list, can lead to unnecessary time and space complexity, especially for sparse graphs. Transitioning to an adjacency list can significantly boost efficiency. Another area where mistakes often occur is in overlooking edge cases. For instance, if there are no prerequisites or if all courses form a single chain of dependencies, these scenarios can lead to incorrect calculations for the minimum semesters. To avoid this, it's essential to include test cases for edge cases like no prerequisites, just one course, or a fully linear dependency chain. From an interview perspective, this problem is a great opportunity to demonstrate your understanding of graph representation. Knowing how to use adjacency lists and traverse graphs efficiently is key. Since this problem is fundamentally a version of topological sorting, you should be ready to explain the algorithm in detail and highlight its use in scheduling tasks. Optimization is another area of focus, especially when constraints like a maximum number of courses per semester are introduced. Interviewers may expect you to leverage BFS or greedy algorithms effectively. Additionally, you should be prepared to discuss the trade-offs between BFS and DFS, particularly why BFS is often better suited for this specific problem. Lastly, clear communication about how you handle edge cases, such as disconnected graphs or missing prerequisites, is critical to demonstrating your problem-solving skills. This problem also connects to several related problems that you might encounter. For instance, Course Schedule, LeetCode 207, focuses on determining whether all courses can be completed given the prerequisites. In Course Schedule 2, LeetCode 210, you need to identify the specific order in which courses should be completed. Another variation, Parallel Courses, LeetCode 1136, involves minimizing the number of semesters without a limit on concurrent courses. And, of course, there's Parallel Courses 2, LeetCode 1494, where the number of concurrent courses is capped, making it more complex. When considering alternative approaches, a DFS with memoization can be used to calculate the longest path in the graph, which corresponds to the minimum semesters. However, this approach can be less intuitive for interviewers and might be harder to explain. Another option is BFS with a priority queue, especially when weighted edges are introduced, such as assigning difficulty levels to courses. This allows you to process courses based on their weights. For advanced variations, dynamic programming with bit masking can be applied to track completed courses and optimize semester assignments. While this approach is more complex, it's worth considering for problems requiring a higher level of optimization. Thanks for following along. We covered the key strategies to solve Parallel Courses 2, highlighted the importance of efficient optimization techniques, and shared practical takeaways. Be sure to practice similar problems to solidify your understanding. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!